Kia ora. I'm Jen, as Caroline's just said. I've got 3 years of funding from the Deep South Science Challenge research grant to look at climate change impacts on the New Zealand energy system. So it's great to be here. I'm literally quite new. I arrived in the last couple of months and I've spent a lot of time just setting up hardware and software and licenses and things so far. My co-researchers on this project are Janet Stevenson and Michael Jack from the university, and Abba Sud and Christian Zammit from NIWA. And I also have the use of an all of New Zealand electricity system model, which I have borrowed from Meridian Energy. And Grant Telfer, who I acknowledge here, is the guru behind that model, and he has done a lot of this work with me over the last couple of years. So I have been doing this work at Meridian Energy, and that's what I'm going to show you. And but this is sort of the foundation from where I spring off and do a whole lot more in this area. So I'm going to rip into it. Looking at the New Zealand energy system over the next few decades, we have to, we always have to keep the energy trilemma in balance and always keep that in the back of our minds as we're looking forward. So the energy trilemma, of course, is looking at security of supply, making sure that the lights don't go out, and whatever the planning is over the next few decades, making sure that we reduce emissions, and also keeping costs in check. So always I have this in the back of my mind when I'm running scenarios on this big model and looking out 30 years and trying to decide what the electricity system is going to look like and what the major impacts are going to be on it. Looking at the emissions side of things, we know that agriculture is about half of New Zealand's emissions. We know that electricity generation is very small in New Zealand. We had 82, 84% renewable over the last couple of years, which is a great foundation for trying to get that higher, but also a great foundation for enabling the reduction of emissions in other sectors by electrifying them. So the Climate Change Commission's draft advice, which came out 2 weeks ago now, was very strong on this. It said one of the best ways to reduce emissions is going to be to electrify a whole lot of stuff. You'll notice here that industrial processes and transport add up to about 26% of New Zealand emissions, and it's mainly these that the focus is going to be on electrifying. So can the New Zealand electricity system support that? And that's one of the questions I'm looking at, whilst also looking at the changes that we can expect over the next few decades in terms of climate changes, wind, water, and demand changes, such as how many EVs there'll be. So let's look at it. This picture here encapsulates the whole New Zealand energy system. So the bottom half of this is renewable and the top half is non-renewable. The left-hand side is electricity and the right-hand side is non-electricity. So you can see that about 20.5% of New Zealand's energy use is renewable electricity, and about 66% of New Zealand's energy use is non-renewable, non-electricity. So the job in front of us is to do this. It's to smudge as much of that big red ball down into that bottom left-hand corner as we can to get rid of those emissions. So as it says there, about half of that big red ball is from transport. So that's going to be a big impact if we can electrify a lot of that. There's also, this is going to happen as well, so this will be things like biomass, biofuels, hydrogen all have a part to play too, that they're going to reduce emissions in these sectors, but they're not electricity obviously, although the hydrogen uses electricity. So how much, that's the smudge that we've got to do, how much and how fast we can do that is uncertain, but that's part of my job over the next few years is modelling this. And whether the New Zealand electricity system can support this transition. So today I'm just going to talk about, I'm a climate scientist by trade. I got my PhD in climate forecasting, so I always come back to that. So I'm going to look at the projected changes to temperatures, water and wind, and the impact that that's going to have on our ability to generate with those fuels. The demand side is really important, of course. How many electric cars are there going to be? What's going to happen to heating and ventilating load? Is there going to be a lot more irrigation, and how much efficiency gains can we expect through better insulation of houses and more efficient appliances? So those are questions that I'm trying to answer as well. And then I'm going to have a look at the modelling that I've already done and look at projections of generation, what new generation plant is going to be supplied, or do I think is going to be supplied to be built to supply that demand? What % renewable can we achieve and how? And what emissions changes result from that? So first of all, temperatures, rainfall, snow, river flows and wind. These are the main fuels in an 82% renewable system. NIWA does some projections of these. They start with the six best global circulation models in the world. They take those and they downscale them all to a regional scale, which is about 20 odd kilometres. And then they downscale them again to about a 5 kilometre grid. Then they put that rainfall data on a 5K grid into a distributed rainfall runoff model and flow it over the surface, and therefore estimate what river flows are going to look like in 50 and 100 years. So to start with temperatures, under a middle-of-the-road emissions scenario, RCP6, we can expect about 1 to 2 degrees warmer over the whole country by the end of the century. We're looking much higher than that at the moment. Under a high emissions scenario, RCP 8.5, we might be looking at 2 to 4 degrees over the whole country. That's going to have big impacts for a whole load of reasons. It impacts our snowpack, the temperatures. It increases air conditioning load in summer. It increases irrigation load in summer generally, although there's other constraints on that, such as resource consent rules and stuff. It impacts our transmission lines because they can only carry so much electricity in summer, and if it gets too hot, they sag too much and get close to vegetation, so they have summer limits on them if it gets too hot. And it also, at the moment, impacts cooling water for thermal plants. So Huntley Power Station shuts down if the river water gets too hot because it can't cool the plant. So all of this increase in temperatures has an impact on all of that. In the future, Huntley is going to convert to just gas, but it will still have a bit of an impact. Rainfall is important, and this is quite a strong impact in New Zealand. Their modelling expects that under a middle-of-the-road emissions scenario, by the end of the century, we're expecting to get 10 to 20% wetter on the west coast, and that is the source of the main big hydro plant in New Zealand, the big hydro catchments, and 5 to 15% drier in the east and north, and that's the down the east coast is the main source of irrigation load. And in summer, in New Zealand, on a hot summer day in late summer, irrigation load is the biggest electricity demand source in some of these areas. So that's pretty important. So this is on an annual basis that these are going to change, but there's going to be a lot of seasonal changes as well. So this is from NIWA's Our Future Climate New Zealand website, the startup. So it shows that over time, and the blue line is the, I've got some of the buttons here, I'm scared I'm going to push the wrong one. The blue line here, the blue line here is now, and NIWA projects from 1970 to 2100 in their models. You can see that while many of the seasons remain fairly flat, they expect winter rainfall on the west coast to get a lot wetter. So there's going to be seasonal changes, which really impacts our ability to generate, because of course currently the highest inflows are in summer, which is when we don't need the electricity, so we have to store them, and the lowest inflows are in winter when we do need the electricity. So some of these changes, seasonal changes in rainfall, are going to impact that. We also expect big increases in volatility. So if you take a parcel of air and you warm it by 1 degree, it can carry 8% more moisture. So by implication, we would expect floods to be 8% bigger because there's more water to come down. It's not quite as simple as that, but that's part of the issue. We're also expecting stronger westerly winds, which will provide more orographic uplift and spillover in the Southern Alps. So we could expect when we get floods that they're going to be bigger. I'll just point out that this is the November 99 flood at the Clyde Dam, and there's two people standing here. And I don't think I would be standing there with that sort of thing. So the access bridge had already been washed out. These people had to leave by climbing steps up the front of the dam and off the side of the dam. And that was 4,300 cubics going through the spillway, and it was designed to carry 4,700, so it was pretty close. So we could expect floods to get bigger, and there's big issues with that, not only in terms of infrastructure, but also in the hydro scheme's ability to use that water and not just spill it all down the river. So we also expect more droughts. These pictures from this report here, they show in 2040 about 5 to 7% more time in drought down the east coast of New Zealand and in the North Island, and about 10% more time by 2080. If we turn that into the number of dry days below a certain level of moisture, you can see that in a high emissions scenario by the end of the century, we would expect about 20 more dry days up in the east coast of the North Island. And Gisborne normally gets about 200 dry days. I think it's less than 0.1 millimetre of rain, 200 of those days a year. So that's increasing by 10% the number of dry days. So in theory, that's going to increase a lot more the irrigation load, although of course, as I've said, you can't just necessarily ramp up and take water out of the river, and there's not necessarily going to be resource consents given for more irrigation. So that's a little bit more complicated than that, but it certainly has an impact. Snowpack changes are quite important. Half of the Waitaki scheme's summer inflows are from snowmelt, so it makes a big difference to the seasonal variation of inflows in that catchment. This is already happening. You can see here Mount Footstool and Mount Cook National Park in late summer 1950 and late summer 2018. That was an extremely dry year, late summer 2018, but it clearly shows that there's been a lot of seasonal snow lost, especially at lower elevations in the last few decades, and we expect that to continue. This is some work by Jordi Hendricks in 2011, which is a bit old now, but it hasn't really been superseded by anyone, showing that by mid-century, perhaps 20% less water stored as snow over the winter in the Southern Alps. And by the end of the century, perhaps 40 to 80% less water stored as snow. So this has a big impact on that, as I say, the seasonal variation of inflows into the hydro lakes. The other complication with snow is because we expect more moisture at elevation. There may be more snow at elevation, but there's certainly going to be a lot less lower down and much higher snow lines. Don't invest in ski fields, but you didn't hear that yet. So that's snow. We also expect changes to ice, to glacial flows from glaciers. So glaciers in the Central South Island provide about 6% of the annual water into the hydro lakes. And that's important because when you think about it, that water has been stored for hundreds of years. So it's really nothing to do with changes of climate. It's due to changes in temperature, of course. But it's sort of bonus water, if you like. It's coming in despite what happens with the weather over your summer or your winter. This is the Franz Josef Glacier in 1867. Lots and lots of ice. And if you watch this ridge here, you can see as I morph this, this is 2018. So a lot of water has gone out of those glaciers already. So this one here is the Tasman Glacier. It looks like a big pile of gravel, and it is. This was 1977. This is all ice covered with 1 to 2 metres of gravel and rocks. And you can see in this one, there's already some sinkholes starting to appear from inglacial streams. I did my master's on this glacier many, many years ago and spent a whole summer wandering all over it, drilling holes in it. So it was great fun. But anyway, this is what it sort of looks like more recently. The two don't match very well, but you can see it's a large lake there. And the expectation is that these big valley glaciers will continue marching up valley at a reasonably steady rate with these proglacial lakes at the bottom. And at some point they'll run dry, they'll have a dry bottom instead of ending in a lake, and they will slow down a bit. But we expect a fair amount of bonus water from those to keep coming into the hydro lakes for a while. So how are the changes to rain, snow and ice going to impact hydro lake inflows? So that's one of the things that I've looked at. So this graph shows Pukaki inflows. Pukaki is the biggest hydro lake in New Zealand. And it shows from July to June on the x-axis and flow and QMAX on the y-axis. The blue line is the long-term average inflow. So it shows you that it's much higher in summer than in winter. This is partly because of rainfall. It is wetter in summer than in winter at this location, but mainly because of that snow pack, which doesn't come down in winter and does melt and come down in summer. So the red dotted line is I've done some modelling on this, and it's my expectation of what will happen to that lake's inflows by 2050, which is only 30 years away. And I expect it to be about 10% lower in summer and about 10% higher in winter. Now, this is a good news story coming out of climate change. There's not many of them, but that is going to much better match demand. So at the moment, we have to store all that water when it comes in the summer so that we can use it in the winter. What's going to happen in future is that the inflows are going to be higher in winter, but also the demand will probably be lower because there'll be less heating needed in winter and more air conditioning load needed in summer. So the two profiles are going to better match in the future, which is good. I've done every hydro scheme in New Zealand. I've modelled this. This is another one, Manapōuri, has similar, much higher in winter and lower or not much change in spring and summer. But by the time you get up to the North Island, it doesn't have the snowpack and hasn't got such big changes in rainfall projected. And so not expecting too much difference in North Island hydro lake inflows. So as I said, I have a big black box, which is the New Zealand electricity system. It's called LPCON. It's a model that I've borrowed from Meridian Energy, and it was created by Grant Telfer. And into it goes all these inputs, both on the demand and the supply side, to try and look at the issues that the electricity system is going to have. We also expect changes to wind. This is a picture of 99th percentile wind in a high emissions scenario by the end of the century. And you can see that we expect it to get much windier in the South Island, up to 10% windier for those strong winds, and less windy in the north of the North Island. So this is not only going to impact generation from the current plant, but also where new wind farms are located. One thing that I've done a little bit of work on is that wind turbines, when it gets too windy, they turn away from the wind so they don't get damaged. And so I looked at whether the increase in wind was going to create a whole load more turbines turning away from the wind and therefore less generation, or just a little bit more wind and therefore turbines would be able to handle it and they would generate with that wind. And the answer was a little bit more generation. It wasn't enough for them to turn away all the time. So this is the data that I put into the model. I have capacity factor for wind for a whole lot of different regions. And then I've got current wind farms in the model, and I build wind farms in the model as they're required in different regions, according to where it's easiest to build them. So building theoretical wind farms, which will probably one day be built. So in Auckland, it's going to get less windy all year. In Wellington, it's going to get less windy in summer and windier in winter and spring, according to NIWA. In Canterbury, slightly less windy in summer and autumn, but windier in winter and spring, with an annual change of about 2.5%. And in Otago, which is the biggest impact, sort of generally, same again, less windy in summer, windier in winter and spring, and an annual change of about 3.6%. So that's the fuel side, the fuel for generation. So now I'm just going to look briefly at demand, what I think is going to happen to demand. We all know that electric vehicles are going gangbusters. I can't believe how many I just see in the street in Dunedin. So that's increasing quite rapidly. And they are mainly for short trips. So they are mainly in the sort of urban areas is where we see them at the moment. And that's because the bigger their range, the more expensive they are. And there's still sort of, I would love to have one, but can't afford it. So I'm watching the price coming down. This is the price. This is from a concept consulting report in 2019 where they tried to imagine how fast they were going to grow EVs. What they're saying here is that this is the cost relative to an internal combustion engine. So the 100 line means that the cost spread over the life of the vehicle is, if it's on the 100 line, it's about the same as an internal combustion engine. So what you can see is that they are predicting that the prices are going to fall, and they're going to fall below the cost of an internal combustion engine. And what they're saying is that a light private vehicle is going to be below the cost of an ICE in the next year or so. Now, that doesn't seem like that when I went to look to the Leaf, and if I wanted a Leaf that could do 200 kilometres on a charge, it was going to cost me $40,000. Whereas I can get a small Toyota petrol car for much, much cheaper than that. But what it's saying is, of course, that the lifetime cost is much cheaper to run the electric vehicle and and maintain it, and that's why they're coming down. But still, people see the nameplate price, and I think we're going to need some incentives from government to really make a difference here. So I have projections in my model of the number of EVs, and I run different scenarios of that to see what the impact will be and whether the grid can handle it. I expect changes to heating and air conditioning load, and these are the numbers that I've put in the model for one of the scenarios that I've done. So increased summer cooling is the blue bars, and reduced winter heating is the green bars. You can see that the increased summer cooling is mainly in Auckland, and the decreased summer heating, winter heating is sort of mainly in the South Island. But the result from this scenario is an extra 160 megawatts on top of peak summer load, and summer load might be 2,500 megawatts or 3,000 megawatts for the whole of New Zealand. So it's a reasonable difference. Also looking at changes to irrigation demand, and as I say, this is a very hard thing to predict because I was speaking to an irrigation engineer who said, look, Canterbury's done, you can't fit any more irrigation in there, there's no more possibility just to fit that infrastructure in there. So don't worry about that. So it's not just contentious, but he said other areas, there will still be a lot of growth. So anyway, this is one scenario where we get a lot more irrigation load in South Canterbury, which is the biggest irrigation electricity demand node. The Ashburton node is where all the irrigation demand goes on a hot summer day. And so possibly 170 megawatt peak on a hot summer day in the future. So yes, right. So this is sort of it all put together in a graph to look at what the total change might be. So this is one of my scenarios again. This is 2018, this is a little bit old, this graph, I need to update it. 43 terawatt hours of electricity generated that year to supply the whole of New Zealand. What I've got here is no increase, so the light green is a reduction in load and the dark green is an increase in load. So what I've got here is a reduction in load for residential electricity demand. That's because we expect more efficient appliances, better insulation, some people with rooftop solar, some people with batteries, time of use pricing. So we expect very soon with all these smart meters coming in that you will be able to use all your power at 2 in the morning where it's really, really cheap and not use it during the day when it's more, or over the evening peak when it's more expensive. Just smart appliances, things like that. So that's going to bring the load down in the residential area in this scenario. I've done a whole lot of different scenarios. Commercial, I think there'll be some reductions and some increases. Just increasing GDP, increasing population will bring in more load in those areas. Same with industrial. We expect more summer cooling and less winter heating. We expect a little bit of extra irrigation load. And we expect a whole lot of electrification from industrial heat plus efficiency gains, and a whole lot of light fleet transport being electrified, but some efficiency gains as well. So that adds up to about a 20 terawatt hour increase. Remember, it takes 43 terawatt hours at the moment to power the whole country for a year. So perhaps a 20 terawatt hour increase in the next 30 years. So keep that number in your head. But we've got a whole lot of plant that's due to retire. So a lot of this is thermal, so it's gas and coal is the grey colours, diesel is red. These are all actual individual plants which are due to retire. A lot of the wind farms will be repowered with new technology, but potentially that's 25 terawatt hours of plant that's disappearing over the next 30 years. So in total, this is what it might look like. So this is total New Zealand electricity demand from 2000 to 2050 by a whole range of agencies, pretty much everyone in New Zealand who's projecting this sort of stuff. And there's obviously a massive range of projections. So baseline demand gives us a little bit. That's increases in population and increases in GDP offset by efficiency gains, but that's actually quite small. The largest impacts are the electrification of transport and industrial heat, changes to heating and air conditioning and irrigation. And all of these people have put those into their modelling, and these are the range of scenarios. So So our lower estimate is about a 13 terawatt hour increase on top of the 43, plus the plant retirements, of course. If the average, but the upper estimate is about 60. So if you start with 43, we're going to be somewhere between 53 and 103 terawatt hours by 2050, which is a very short period of time. The average current wind farm produces about 0.5 terawatt hours a year, but new turbines are going to be bigger and more efficient. So we might need between 10 and 60 new wind farms by 2050, which is a massive build program. Each one takes years of planning, commercial aspects, getting turbines booked in from overseas. It's a massive build program. But of course, we won't just build wind farms. That's just to give you an idea of the size of the problem. What will we build? Well, if we based it just on cost, then this is what we might build. So this is the levelised cost of energy over from sort of the late 90s to looking forward into the future. And these are the costs pretty much today. So you can see that this green line is onshore wind, has been coming down gently over the last 20 years. One of the first wind farms in New Zealand, Te Apiti, was built in 2004 and it cost about $110 a megawatt hour. As I say, that's the cost of building the plant spread over the lifetime of the plant. But this here is grid solar, this orange line falling from the sky. And that's largely because China is building so much grid solar. They're just going gangbusters and the price is falling and falling. And these are the prices today. So what becomes clear is that renewables are outcompeting non-renewables clearly at the moment. And so if you just went on price, then you would only be building renewables from now, regardless of government policy. Right, so I'll just talk briefly about the modelling that I do. These are some of the inputs that have been going into it, and this is the modelling. I've got this LPCON, this model of the New Zealand power system owned by Meridian Energy. So it uses a linear programming construct to match demand and supply on a fine temporal and spatial scale and produces an efficient, least cost energy system. That's what it does. It's got a spatial resolution of either nodal, that's every grid exit point where the power exits the main transmission grid. There's 260 nodes. You can run it like that. It takes about 5 hours. You can run it regionally with 22 regions, and that takes about an hour. Or you can run it by island, and that takes about 15 minutes. So it's got a 30-year lead time, weekly granularity, but it's got 15 block low duration curve representation of within week variation, and you need that because the evening peak in winter is the real thing that you're trying to predict. So we couldn't run it on a half-hourly basis. It would take about 6 months to run. So we do that by breaking the demand down into blocks, and one of those blocks represents the evening winter peak and one represents the summer low point, and so that's what you're predicting. It's got 86 years of hydrological data and wind for every hydro catchment or area in the country, and it's got representation of things like price, the cost to generate, offers into the electricity market by all the different players. It's got generation capacity, so that's both all the current hydro, wind, coal, gas and geothermal and solar, but also projected, so hypothetical plant going forward. It's got hydro storage, inflows past and future. It's got hydrological constraints, cascading releases down rivers, minimum flows, consent conditions, spill. It's got all of that in it. It's got electricity demand projections, as I said. It's got a transmission network. So it's got things in that like line flows, line losses. We lose, if you send power from Manapōuri Power Station to Auckland, you lose 7% of it along the way, just for it draining away into the ground. So it's got that in there. It's also got summer and winter line weights, line constraints, summer heating line constraints. It's got dynamic system risk, fast and slow reserves, planned and forced outages for all plant and transmission lines, and demand response. So demand response is where people come home with their electric vehicle at 6 p.m, plug it in, but it doesn't turn on until 2 in the morning. So that is going to have to become part of our system, and I'll talk about that more in a minute. The main two scenarios I've been working on is this. Evolution and revolution. Evolution is a modest decarbonisation emissions reduction scenario. We keep a little bit of gas peaking plant. We get to about 95% renewable or above, and the carbon price remains fairly low. The revolution scenario is strong decarbonisation, no thermal plant remains. We go to 100% renewable, and the carbon price is relatively high, although I think I'm going to push it even higher than that. That's what it's looking like. So the results from that is this. This is one scenario. So this is the revolution scenario. It's a strong decarbonisation scenario. It goes to 100% renewable. So the red dotted line is 100% renewable. Oh, sorry, it goes to 100% renewable. This goes from 2019, I ran this then out to 2049. And it's got annual generation for the country there, and each block is 1 year. So you can see what happens here is hydro doesn't really change. I don't have any new big hydro in my modelling. I just think it cannot get past resource consent. Onslow pump storage scheme may be an exception to this because the government may push it through, but there has been nobody succeed in flooding a river valley in the last 20 years. There is a small amount of new small run-of-the-river hydro in there, which I think still will get consented. The wind is the light green. You can see that grows like topsy. Geothermal, we get a bit of extra geothermal. There's a bit of resource still available in the North Island, and that will probably be closed cycle geothermal in the future. So that is the emissions are put back into the ground because they do have some carbon emissions. You can see the orange thermal plant all dies out in this scenario, and grid solar, this bright yellow, grows quite fast. And generally, of course, total demand grows from 43 up to about 60 terawatt hours. The things that are important here is the red bit here, demand response, that's available all the way through here. And you can't see it very clearly on this annual basis, but what this scenario has is in the middle of winter on a really cold evening, when everyone comes home and turns on their heaters in the oven, we need demand response to get through that. Otherwise, we have to overbuild. It's got up to 1,500 megawatts of demand response in there, which is quite massive. That means all of the stuff will be done automatically. People will come home and plug their car in and walk away, put their clothing in the dryer and walk away, but the device won't turn on until 2 in the morning. So that will, and people will be paid for that. There's also industrial demand response, which is already happening. So particularly big refrigeration units can turn off for an hour with no problem at all if they're well insulated. And so that's already happening. People are already being paid to provide that service. Generally, though, because of grid congestion rather than a shortage of supply at the moment. So that's stuff that's going to happen in the future. And what you can't see on here is we need some batteries as well to help us just through that tiny little period in the winter and the evening peak. This is the percent renewable. In these two scenarios, we get to 95% and 100% renewable by the early 2030s without too much problem, provided we've got this demand response capability, which has got a question mark over it, whether we can get there. I just wrote an article in the conversation a couple of days ago where I was saying I don't think we should be aiming for 2030 100% renewable. The Interim Climate Change Commission has said that that will be extremely expensive. If we try and do that too soon, we need to slow down and bring it in slowly, keep a tiny bit of gas peaking available so that we don't have to overbuild just to provide that tiny little 2-hour period in the middle of winter when we need a lot of load. And the Climate Change Commission has agreed with that, but the government is pushing ahead with 100% renewable by 2030. Megan Woods has said, but I think it's the wrong move. I think it's going to be extremely expensive and quite difficult. So we do see that that's possible. This is carbon emissions just from electricity, which I calculate from electricity generation, but not from reduction in carbon emissions from electrification of transport or anything. So you can see that carbon emissions from electricity peaked in 2006 and they've been falling ever since. And we expect under these scenarios that they will continue to fall and that the big step changes will be when the big thermal plant retires, the big coal plant. So almost there, this is the second to last slide. This is the same picture as before, but on a weekly basis. So so it shows us the same thing. It shows us time along the x-axis out to 2050 and the energy needed per week on the y-axis. It shows the colours, which are slightly moved around, but the blue is hydro, the light green is wind, the yellow is solar, grid solar, and the green is geothermal, same as. But what it shows you is the seasonal fluctuations up and down. And the important things here are the purple, which is battery discharge. So it shows you by sort of 2030, we're going to be needing significant amounts of battery use once again for the evening peak in winter. So people will charge them up. They'll either be household batteries, so people will charge them up with their solar panels during the day and then release them over that evening peak, or it'll be industrial or large grid-scale size batteries, which are already being investigated in New Zealand. I think there's going to be one within the next year in New Zealand. And the little black line is demand response. Once again, it doesn't look like much, but when it's needed, it's really needed. It will be big. So it's hard to see on this graph. The red dotted lines are price in the wholesale electricity market. So the thing to note is that average price remains the same or drops away, because as more and more cheaper renewables are built and they get cheaper to build, it should come down in theory. But the other thing to notice is the weekly price is much more volatile than it has been in the past. And that's because when there's no water and no wind, and it's dark and it's cloudy, the price is going to go skyrocket. That's if the current market model prevails, which who knows what the future brings. So just in summary, we're expecting significant changes to the New Zealand energy system over coming decades, both on the supply side and on the demand side. Our modelling indicates that the electricity system will continue to decarbonise itself because it's the most efficient outcome. It will also enable the decarbonisation of a significant portion of transport and industry, and the power system as a whole will become dominated by increasing levels of renewable generation over time. We're going to get increasing intermittency from wind and solar being a larger portion of the system, and we need the big battery banks of the big old hydros to back that up, so you hold the water back when the wind's blowing, and when the wind stops, you open the gates and let the water go. And that's really the only way we can get to this high level of renewables. But it will require some gas peaking plant over the medium term while we get ourselves sorted. Retention of hydro capability and flexibility. I don't think we want to lose any of those hydros now they're there. And particularly hydro storage as the battery bank. Behind the meter technology, demand side participation and storage, including rooftop solar batteries, vehicle to grid, battery electric vehicles, person to person. So things like households sharing batteries and using them at different times, electric vehicles plugging in and the system using their battery power, what they've got left at the end of the day, and then which is vehicle to grid, and all sorts of different batteries, and grid load as well, grid size batteries as well, and smart meters, smart appliances. And that will supplement rather than challenge grid level generation supply, I think. And significant new generation build planning and investments needed. It has reasonably long lead times. And some of these plants, some of the hydro plant we use is over 100 years old. So these things are they take a long time to build and get financed, and then they last for a long, long time. So what we need is some certainty around consenting and government policy, bipartisan agreement between the government parties, so that we can get investing, I think. And we're likely to see new markets emerging. Demand response markets are probably on the way, where you can bid in, or a big like a steel mill or a big refrigeration or a big other big demand sources can bid into the market.